The last session, we'll start with Byron Cook, VP and Distinguished Engineer at AWS, where he gave food and shelter to a lot of us in this room, and he gives us shirts. He has been there for coming up to 10 years now, almost 10 years. Before that, he was at Microsoft, which we had already working on termination proofs with Andreas, which was basically the reason why all the PhD students in this room didn't see Andreas in Freiburg, because he was always in London working with Byron. So I'm looking forward to your talk.
All right, great. Thanks very much. Thanks. Martin encouraged me to submit, and he said, submit something that's beautiful, but maybe not very useful, right? It doesn't need to be useful. Just make sure it's beautiful. So we've been to this thing. I think it's potentially quite beautiful. I think that there's some structure, Andres, that you'll enjoy. I also think that if I'm right, it'll also be disruptive, and I know you like to be disruptive and troublesome. So that should appeal to you. Okay, sure. Sure. It's also, there's some, I think you might see and enjoy some similarity in outline to prior work, which I think was also very disruptive to the conventional wisdoms at the time. So that led to this Scientific American article about the work. There were many papers where this, I have a picture of you, Lenore, yeah. So 2004 at ETAPS, apparently, according to the internet. Yeah. So where I first met Andres was at ETAPS in Barcelona, where I didn't know Andres when he was at Microsoft. We missed each other, but then I told him I was going to be moving to Europe. So then he encouraged me to come to the Schloss Ringberg workshop that Lenore mentioned. So that was an. That's right. Okay. Anyway, so we had very good discussions. I was invited to come to Saarbrücken and work with Andre, and that's kind of where the magic began. So then we. I didn't co-chair very well, so. I did co-chair VMCI. And we met in Paris quite a bit. Those were, I think, really amazing times in London, Paris, Germany. So thanks very much. So that's the end of the gushy bit. So let me tell you about this work that we've submitted. I wanted to tell you a bit about the motivation. I'll probably spend about 10 minutes there, and then I'll give you an illustrative example. The details are in the paper, but the high level is that we're distributing SMT solving. We're getting pretty exciting results distributing an SMT solving, and that raises the question of whether or not we could or should be doing something different with regards to quantifiers. So as you may know, Amazon is a big investor in automated reasoning on formal methods. It's important to enterprise customers. We have a number of customer-facing features. Billions of calls per day to the solvers. We've done proofs about a bunch of open source code, from FreeRTOS to the encryption SDK to something called AWS libcrypto. And then we're doing lots of proofs internally to Amazon. So practically every bit of code is either directly or indirectly touched by proof these days. So all services use networking, virtualization, storage, cryptography. We're doing, in some way, we're doing proof about all of those pieces, and then everything's kind of built on top of that. Under the hood are automated theorem provers. A couple of years ago, we launched something internally called the Amazon Trusted Solver. And this is a cloud scale service. So I'll just show you kind of what it looks like at the command line. So you could call it like CVC5. Here I give it a file, and then it gives you an ID that then you can do various things with, right? You could ask what's the status of it. You could kill the job. You could do all the things you could probably imagine. You can also set up different solver configurations to like race them, for example, so you can compete, or you could run them in a way where you get the results from both of the solvers and then make sure that they give you the same answer. And so this is it began its life when a service team in AWS that was building an automated reasoning based tool used Z3 with a flag that everyone knew was unsound, right? If you talk to the developers of Z3, you knew the answer wasn't right, and it caused a very bad day for a bunch of people. So we realized that we needed to wrangle the usage of solvers into a more central place, such that we can make sure that people were calling it correctly. But we've also learned that it's great for using this style is great for collecting telemetry and helps us make decisions about where we're going to invest. But then also the really amazing thing is it helps facilitate the move to distributed proof search. So I'll say a little bit more about that. So here are the provers that it currently supports. And if you're a prover solver kind of person, you probably know all of them. You may not know NFA2SAT, but that's not really the point of this talk. The point is about this one. So the A4 is sort of a code name for a distributed solver. And the question is, can we meaningfully distribute solving across thousands of machines to improve the latency? And we're really inspired by this work of Malab Mono. So hold up your hand if you know Malab. Yeah, so not many people. This is like, I don't know, this is like, it's a real game changer. So to give you an illustration of how amazing this is. So this is a graph you've probably seen before. This is all, or some version of this. This is all of the winners of the international SAT competition from when the SAT competition began until 2020. And they're compared on the same hardware and the same benchmarks. So you can see over time, the solvers are getting better and better and better. Okay, and then to read this, I mean, hold up your hand if you know this kind of graph. Do I need to explain this graph? Yeah, I'll just say a couple words. So here, this solver at the top, this is saying that there's about approximately 250 instances that could be solved in 200 seconds. So that's better than this solver, which can solve only about 100 benchmarks each under 200 seconds. You want to be on the top, not the bottom. And right, so I said that. So this is basically 20 years of progress in SAT research, and then this Malab Mono is this new distributed solver, which just blows away 20 years of research. Now it uses a lot more computation, right? Because you're using many solvers. So we've moved from a sequential to a distributed solver. So definitely this is not an apples to apples comparison anymore. But basically this new distributed solver class gives you a new capability that you really didn't see before. We're also seeing similar results for SMT. This work is considerably more preliminary, so I won't go into the detail. So just a little bit of details on how that works internally. So this sort of table stakes idea of distributing solving is just to use a portfolio. So this is this compete mode where you just run multiple solvers, perhaps with multiple configurations. So imagine you have some file F and you want to pass it to a solver. You could pass it to one solver, or you could pass it to a whole bunch of solvers. Maybe you seed them all with slightly different numbers to kind of get them into different states, and then or you could shuffle them. But basically, the horizontal scale gives you more chances to succeed. That's the idea of portfolio. But then what you can do, and this is what Malab Mono is doing, is you could share the conflict clauses between the solvers. So basically, the lessons learned, and it's something like, I don't know if you've ever done, like you've sort of these group exercises where you have small teams all trying to solve some sort of puzzle, but they're in the same room together, and they can solve someone in that team will be able to solve the problem faster because they're learning they're seeing that the other teams have some method they're using, they're getting a bit of success with, so that you can basically copy the ideas from the other teams. And it's the same idea here, that you basically have the solvers running independently, but they're sharing the lessons learned, and there's a bit of work to decide on what to share and what not to share, and when to share it and so on, but it's a good idea overall. And so one of the things I really like about it is that basically good decisions pay compounding interest early. So imagine you get a good decision, like a SAT solver decision here, then because the learnings are shared, you get to the good decision 2 sooner. And because of that, you get to decision 3 sooner, and 4 sooner, and 5 sooner, et cetera. So there's more opportunities for good decisions in this distributed environment. And furthermore, the bad decisions don't cost you as much. So imagine that we had a few solvers that ultimately didn't contribute anything to the final answer. Well, that's no big deal. We just throw them away. So when I Google German prison cell, this is the photo I got. So I'm using this as an analogy. So that I think that basically until now, solvers, SMT solvers and SAT solvers have been written as if to operate in prison, right? They're not going to have any, they're not going to have multiple microprocessors. They're not going to have networking. They're not going to have persistent storage. There's just a bunch of capabilities they don't have access to. And with the distributed, suddenly you just have open space, right? So you can do whatever you want to do. And so you have more resources, more freedom, more opportunity for exploration and failure. We're especially excited about the work in just quantified, using this for quantified formula, where there's basically, if you're trying to solve quantified formula, it's there's really not, like, you have to make a bunch of really difficult choices early on, and you're probably going to make them wrong. So then you have to write the solver extremely conservatively, and thus things don't tend to work out very well. So I'd say the Achilles heel of SMT solvers are quantified formula. Okay, so that's the context. We want to revisit how we handle quantifiers in SMT while keeping the idea of cloud native solving. Imagine we're going to build a cloud native solver, not a sequential solver, and use that in place. Okay, so that's the context of this work. So let me illustrate with an example. So here's a formula that we're trying to answer: is this satisfiable or unsatisfiable? And okay, so I'm gonna do a series of steps to kind of illustrate this idea. So we're gonna translate this into an equisatisfiable form specifically for our approach. So bear with me for a second as we do a few steps. So I'm going to first use we're gonna remove the quantifier using an equivalence that holds in Hilbert's epsilon calculus. So we're basically going to replace the existential with using this. So let me just read this to you. So the existence of X such that not P of holds is the same as not P of holding on the X that we chose such that not P of holds. That's an equivalence that you can that Hilbert's epsilon calculus gives you. So we're doing that translation to get rid of the quantifier. Okay, you'll see why in a few minutes. The next thing we can do is we can translate this, and this is equisatisfiable. And so again, we're doing this for kind of a quite specific reason. So I'm introducing a new logical constant I'm calling L1, which is set. I'm mapping to the Hilbert term, and then I'm replacing the use of the choose term with L1. And I'm using conjunction to break this apart. Okay, I'm gonna basically apply the same trick again. So but now for the universal. So for all X such that Q holds is the same as Q on the X that's chosen such that not Q holds. And so the idea with the choose is that if there is no if there is no X such that not Q holds, then it chooses any value. And so if you kind of puzzle about this for a few minutes, you'll actually see that those are equivalent. So we're going to apply that same approach. The details are going to get a little tricky here. It's because Q in our case is P of X and not P of L1. I'm just deriving this from the formula. So we apply that transformation again, and then I'm going to do that same equisatisfiability trick where I introduce a new logical constant L2, and then I break things apart. Okay, so that's our formula. So why is this nice? So the thing on the left is a quantifier-free SMT abstraction, and the thing on the right is all conjunctive epsilon theory, and that's going to have some advantages. This is the sum total of, this is all of the axioms you could ever add. So it's saying Q of T, for Q of T implies Q of choose a Q such that X holds, where Q is any well-formed formula, T is any term, and X is a variable. And so so how we prove this formula unsatisfiable is we find axioms, conjoin them onto this, and then show that becomes unsatisfiable. And it turns out we're going to be able to do that without in the SMT solver such that it doesn't need to understand quantifiers. Okay, so refinement is just the search for relevant axioms, which can be expressed as refinements in the quantifier-free abstraction. So here's an example. I'm going to leave T free for a moment. We'll talk about that in a moment. So I can conjoin on to this this new formula, and this is derived from the axiom schema. And well, I'll fill in the details a little bit. I haven't told you what T is, but just bear with me for a moment. So this abstraction is free from epsilon theory, and there has no quantifiers. Okay, so I've basically now abstracted away a lot of those details that we're trying to get rid of in this, and we could actually reason about this in pure, as long as I consider L2 and L1 as essentially uninterpreted logical constants. This is now entirely SMT. Okay, now we're free to choose any T so long as it's a well-formed term. Now let me just show you how I built this. So this formula is based on this axiom schema. Let me just show you that to make sure that you agree. The Q in this instance is from before. We can choose any Q, but it turns out that there's only so many Qs that would work. And then this sort of falls out. So it turns out that, I know the details get a little hairy here, but so L2 is basically choose X such that Q of X holds. So that's why I'm able to get from here to here. Okay. Great. So now let's choose a T. And so here I'm just going to do a bit of magic. So bear with me. I'm just going to choose L1. Okay, that's the one bit of magic I have to do. Okay, so now this quantifier-free, epsilon-free abstraction is now unsatisfiable. Why is that? Well, P of L1 and not P of L1 is false. And then, of course, the negation of false is true. And then true of implies something is then just the something. And then if you'll notice, this formula is just the negation of this formula. So now we're done. So we just proved that our original formula is unsatisfiable via an abstraction to essentially a quantifier-free and epsilon-free SMT formula. And we've used the structure of the epsilon axioms to derive the abstractions that we needed. So we basically were doing the refinement in epsilon, and then we're doing the solving without epsilon, and there's no quantifiers in there. Okay, I basically said that. Okay, so then this is something I find quite intriguing, that the syntactically from L1 and L2, this is your axiom schemas. This is the space you need to search over for that and the T, right? Because this is totally defined by what's here in our set. So the only choice we really have is T. So we basically produce axioms of this shape, which is syntactically already predefined. We have two axiom schemas. We can generate a bunch of them, and then we just need to choose the T's for each one, and that's really our only degree of freedom, which I find quite charming. So just to give you an idea, I'm not. This is motivated by the sort of move to distributed, but I'm just going to show you a sequential algorithm so you get the idea. All right, so this is limited to unsat, and we're just going to walk this formula through. So we take the formula, we abstract away, so that gives us our SMT abstraction using L1 and L2, which are uninterpreted here. This M represents the axiom schemas and the mapping from the logical constants to our interpretation over in the Hilbert's epsilon, and then we assert in the SMT solver that SMT formula, and then basically we just solve, right? And if it's satisfiable, we get a model. We can do a bit of work. I don't want to get too into the details, but it chooses the schema that's relevant to the model. And then uses the axiom schema to instantiate term and Q. We assert that. We go back and resolve, and now we're done. So basically, this is an algorithm that kind of implemented the example that I walked you through. Now, what I'm excited about is actually distributing, right? So one could imagine, and here I'm waving in my hands quite a bit, but one could imagine, having 3 or 10 or hundreds or thousands of loops all iterating on this procedure over a shared data structure of, some of these data structures would become shared. Maybe some of them are eventually consistent. Doesn't really matter. Okay, is this beautiful? I think so, because unlike other SMT methods for quantifiers, we preserve the propositional structure in the formula. So I think this is quite nice, right? Here's a quantified formula, here's the abstracted formula, we get to keep this negation here, we get to keep the and here. So we preserve the structure, and thus if we have a really large formula with quantifiers nested all over, we're not doing some sort of transformation where we're pushing the quantifiers around and or so on. We're keeping things where they were, but we get to keep the propositional structure. It's a bit different. I don't know if it's going to turn out to be a massive advantage, but I think it's charming. And then, as I said, it gives a rise to an abstraction into SMT. Which I suspect will be of a benefit, but I don't know that for sure. I think it's charming that the space of possible refinements is just these T's. I basically said that. So if you compare this to previous approaches such as like E-matching or the model-based instantiation methods, I don't know how to really define this, but those methods feel much more operational, right? You look at a data structure, like with the E-matching, you look at the current data structure, you walk over it, you sort of pattern match for certain things, and then you're trying to mine that structure for refinements, and the same with the model-based instantiation method. And I think that the structure of the Hilbert epsilon defines the space of refinements in a way that I think is less operational, and I think will be more easily parallelized or distributed. And then if you sort of compare to skolomization, what I like is that we're left with this partitioning, right? So the skolomization tends to, I think skolomization has a place it's doing something also quite important, and maybe some to make it. So one thing is you could use mixtures of these techniques. So it may be that for certain parts of the formula you can apply this technique, other parts of the formula you can apply skolomization. But I think it's I like the fact that you've partitioned the thing into two parts, where you have just conjunctions of epsilon formulae, and then the propositional piece of the structure independently. Okay, is this useful? I don't know. Okay, so now just to have one more sort of gushy slide on sentiment. So things I think are really amazing about Andreas is his relentless pursuit of developing ideas. We were talking about it during lunch, that the quote that sticks in my head is, "But Byron, have we got to the essence of the problem?" Or "Tell me the story again. What are we doing again?" So I remember, like in the Terminator days, it would just be over and over and over again with him pushing harder and trying to get to the essence and boiling away all the parts that were sort of like they were there, they were in it was sort of like that's just sort of details. What's the essence of the story? And I find that really charming. I think that Andreas is extremely sharing of his resources and his time. He just met some, multiple times I've seen him be very selfless and share things, and people didn't realize he was doing that work, and it made people around him better. Incredibly insightful and creative. I think that we see that from work on SLAM and work on Terminator, that the insight and the creativity is pretty outstanding. He's also incredibly funny. If you know him, you know he's funny. In fact, I'd say 75% of the mails I read from him make me laugh. That's I considered sharing them as screenshots, but then I thought that might be inappropriate because many of the emails are ridiculously inappropriate. And so I feel very fortunate to have met Andreas when I did at the stage of my career I was, because he really taught me a lot about how to do research, how to write, how to think, and I think it's really helped me in my career along the way. So thank you very much.
Questions for Byron?
That's in my office. That's in my office in East London, in Queen Mary.
In practice, when you're doing this distributed solving,
Yeah.
what is the limiting factor? Is it the solving that you're doing in each of the compute nodes, or is it the communication between them?
I don't have, I'm not going to be able to give you an authoritative answer on that because we're trying to figure that out. Like there's cases where it's either. One thing, yeah. Yeah, I think it'll change over time. So I don't think the dust is settled enough to say that reliably.
Do you think a different computer architecture, like a GPU or a cluster of GPUs, could help?
Potentially, I am. So at Amazon, we're building our own hardware, accelerators for machine learning, and actually we're on multiple projects actually working with that team. So proving the correctness of some of the hardware and also proving properties of the compiler. And a part of my motivation for wanting to work with that team is to sort of build up enough trust with them I can start bugging them about these questions. Yeah. So it is my belief. Let me say it more generally. I believe that sort of planning as a so lots of intriguing facts. Like James Bornhold has this paper where the fastest SMT solver is actually on an iPhone because of the memory architecture on the iPhone. So there's something around what hardware support would you need to make things fast. But our first challenge is I'd say the bigger challenge we have is to the volume, the addressable market of this. Like we're getting 1 billion calls per day or whatever, 5 billion calls per day to the solvers. That's not really at the volume to justify starting to burn hardware yet. So. Okay.
Oh, I had a question whether you see this distributed solving, you could also imagine like distributed model checking or distributed verification, like push it up one more level maybe. Like, do you think that, I understand why you're doing the solving specifically, but do you think that same idea could hold?
I'm a strong believer in it, and I have no experimental evidence to justify my excitement. It makes intuitive sense to me. There's a Francesco at Facebook had essentially a distributed abstract interpretation, and he swears by it, and it seems like the results are good. I don't have those results. And then, I mean, the challenge is of course, like I remember when Tom and I were doing SLAM, I don't remember, Tom, if you remember this, that Bill Gates came to look at the SLAM, like there was a tech fest. So Bill Gates came in, there was a graph of like, here's all the driver properties and here's all the big table. And he's like, so if you had 200 machines, you could do it faster? And I'm like, yeah. And he's like, do you want 200 machines? And I just thought about keeping Windows NT up to date. And I'm like, no, absolutely. I do not. Yeah, exactly. So that's kind of what I'm saying, is that there's sort of there's embarrassing levels of parallelization available to us. But yeah, I am a strong believer that ultimately we'll find. I think there's some work here. I don't want to turn this into a talk about Dirk's work rather than my own, but you might talk to Dirk, because I think Dirk has some preliminary results that might be kind of interesting there.
So I would like to know what are what is the, let's say, the power of these reduction techniques, that because you have shown on an example with the, let's say, one alternation, but how far one can apply this? Is this a general technique that you can apply it for a fragment of logic, or?
It's a way. I mean, it's I believe it's as expressive as first order logic. So it
can handle everything. Like, you can handle everything. Like
that's my belief. Yeah, that's from what I'm reading and seeing. That's true. My implementation of this approach right now is me with VI substituting characters. So these characters get really hairy. Like the syntactic details of this approach get really hairy very quickly. So it breaks your brain. So what I need to do is to implement it to see it. But in terms of in theory, I believe it's. I mean, Hilbert developed this as a semantics for first order logic. Yeah.
Okay, and now in terms of practical impact. So when you distribute, how the structure of the formula, I may have equivalent, let's say, formulas having different structures, but maybe the distribution of their, satisfiability problem can be more or less easier. I don't know.
So I think, I'm not sure if I understood your question, but let me answer another question I get that's very similar to that one, and then you can come back at me if that wasn't. So there's a technique from Byron Cook where rather than having a bunch of machines all operating on the same query and then sharing conflict clauses, what he does is it's called cube and conquer, where he looks for cuts. He looks for formulae where he can break the two things apart. And then now you've partitioned this piece of the space on this solver and this piece of the space on that solver, and then you can put the results together in a pretty natural way. And he's getting really big results there. So like he's proved the Pythagorean triples problem with that approach. And I think he has a new proof of the happy endings problem, which I think is with that approach. But it takes Byron Cook to run it, right? So basically what he does is he runs a look ahead solver, kind of looks for the patterns, finds some cuts, and then breaks the problem apart, and does that. And so if you can kind of do that early, I think it's great. But it's hard to get a good partitioning. So this approach is nice because it kind of finds their partitioning dynamically, if you will.
Yeah. Apologies, naive questions. I'm not from an SMT background, but the CVC5 folks have recently talked about distributed and sort of centralized within the different theories. So maintaining like one kind of E-graph representation. And they've got this switch, right, that you can turn this on and off. So you've talked about distribution at a higher level.
Yes.
Is there call for distribution internally?
Yeah. So actually, this distributing SMT work is joint with them. They're Andy Reynolds and Clark are both Amazon scholars with us in the team. But yeah, it is also my belief. Yeah. So basically, if you look at the Nelson-Oppen result around, you can have multiple decision procedures and they're sharing over shared equalities, that sort of streams distribution, right? Because now you have something like egg, the E-graph, maybe make that into a distributed data structure, and then you just build your thing over egg, which to me seems very appealing. So yeah, yay, distribution. Yeah.
I guess we have to move on to the next one. Thank you again, Byron.
Thanks.